the more the computation complex. So here we have the first algorithm is the PNMS, which uses an ad hoc rule using maximum function to assign the gains. But due to using this maximum function, the result is that few tabs are receiving most of the gain, the available efficient gain, and most of the other tabs receive smaller gains, which is even smaller than the NMS algorithm, resulting in decreased speed of conversions and lower steady state even after the initial fast conversions. So there has been a lot of other algorithms that have been proposed to solve this problem. For example, the PNMS algorithm, which combines alternates between the PNMS and NMS adaptation or updates in the iterations. The improved PNMS combines the even distribution of the NMS with the proportional distribution. And there has been more solutions, for example, the new low MP-NMS algorithm, which tries to compress the magnitude of the coefficients before using them to assign the gain, so that it gives more emphasis to smaller coefficients to give them more gains, so that it overcomes the problem of the PNMS algorithm. And the segment PNMS algorithm is just a cheap implementation by making an approximation for the logarithmic function by two-line segment function. More techniques have been proposed, like adaptive mu law, where the constant coefficients are varied according depending on the mean square error. And there's the sparseness controlled algorithms that use a sparseness measure to vary the proportionality parameter in the PNMS, and it has been incorporated into two other algorithms. The complexity, the problem with this algorithm is that there is an increased complexity as we go forward. Another way to look at the variable individual step size is to use an estimate of the gradient, the change or the variation in the coefficients, rather than only the estimated magnitude, to provide the step size for each coefficient. So here, a time estimate, an estimate of the gradient is computed by subtracting a time average estimate of the coefficient values from the current estimate of the coefficient value. So this is an estimate of the gradient that is used. And the only algorithm that is in the literature that uses this technique is the generalized gradient PNMS algorithm, which uses an even distribution combined with a proportional distribution to provide the gain update. So to address the speeding up the tracking, we propose the gradient-induced technique. So it depends on the assumption that coefficients that have large magnitudes will most probably vary in large amounts as well. So if we combine the proportional gain with the gradient gain, we can achieve better results. So this technique will increase the tracking by exploiting both the magnitude, the changes in the magnitude of the coefficient, as well as the magnitude itself. Another problem to be solved here is to have both accurate estimation of the coefficients along with increasing the tracking speed. And in this problem, we use a thresholding technique, and it's incorporated into the NMS and the non-parametric variable step-size NMS algorithm. So if we have the thresholding happening to the coefficient, so if we make this coefficient 0, we stop its adaptation or omit its adaptation, we may probably have a smaller omission error than a larger estimation error, resulting in an overall improved error in the estimation of the impulse response. And by as well doing the same thing for all the coefficients that are thresholded here, we have the corresponding vector elements masked at the input because it's not going to be used when we do the convolution. Then this will effectively increase the step size, since in the normalized NMS, the step size is normalized by the power of the input signal. And this is incorporated into the non-parametric variable step size as well. And this provides an overall improvement. So it improves the tracking speed, it improves the steady state performance. So in order to be able to do this, since I'm focusing on hands-free smartphone applications or like echo cancellation, I have measured 2 impulse responses from a smartphone, and I measured one in space, on its face, and space on its back. And these were the resulting impulse responses. So if we have a closer look here, we find the great changes in the magnitudes of the coefficients, trying to mimic a non-stationary or highly non-stationary scenario. So in the gradient-induced technique, the 2 impulse responses were used sequentially. So this dip is where the input response changes, and the PMS is used as a benchmark for comparing other algorithms. So here we have the gradient, generalized gradient PNS, which provides improved tracking. But even with the gradient-induced PNS, we can see here an obvious improvement in the performance, at least 3 decibels. And by incorporating the same technique into different PNS-based algorithms, we can see an improvement in the tracking performance. So here I show a couple of algorithms. And the last results for this contribution is trying to incorporate the GPNS into the cheaper implementation of this algorithm to achieve same or even better performance when compared to the more expensive MEP-NMS algorithm. So in the GSP-NMS algorithm, we don't need any logarithmic computations, but this algorithm requires logarithmic computations. And this is the resulting publication for this contribution. The next contribution is the threshold and masked NMS algorithms. So here, a threshold is deduced from the step size, showing an improvement in the steady state performance because smaller coefficients are not introducing those errors anymore. And by even adding the masking to the algorithm, we have an improved tracking speed due to an effective increase in the step size. So these are the results for the LLMS by converting it into the non-parametric variable step size. We have a variable step size here, and therefore the threshold as well is time varying. So there is an improvement in the performance, as well as by adding the masking. But we have here a problem that the steady state levels off earlier than the non-parametric variable step size. And this is because the threshold is a fixed ratio of the step size, which makes some of the coefficients stay thresholded and they do not contribute at all. They are thresholded at 0 and they do not contribute at all. So we overcome this problem by making the error ratio as well time vary, so it decreases over time, such that the small valued coefficients have the chance to converge into their values after the larger ones. And these are the results for both algorithms, showing an improvement of around 4 to 5 decibels in the tracking performance. And the steady state increases as well. I have designed a MATLAB GUI simulation environment for adding as much as input responses as we want and comparing different algorithms. So here I've implemented a lot of algorithms, some of which are shown in the presentation, some of which that I didn't even include in the pieces. And we can compare the performances and can even switch into the progress in the adaptation of the input responses themselves. So measurement of linear acoustic echo path responses were carried out in this research for a smartphone. We can measure more. And the gradient-induced technique is introduced and incorporated into PNMS-based algorithms, which provides up to 4 dB improvement in tracking speeds. And the threshold technique improved the tracking speed from 5 to 8 dB on average for the LLMS, as well as 4 to 5 dB for the LLMS in the steady-state performance. And the threshold technique was as well incorporated into a variable step size algorithm, which is the state-of-the-art in the literature, the non-parametric variable step size. And it provides from 5 to 7 decibels on average improvement in the tracking speed, but no improvement in the steady state. And this problem was dealt with by making the error ratio time varying as well in the adaptive threshold with NLP, NPVSS, LMS algorithms, and it provides both faster tracking and improved or increased steady-state performance. In the future work, we can try to evaluate the performance of these algorithms using speech signals, because I've used only white Gaussian noise signals. And we can have more scenarios for the phone. So I just had the phone placed on its face and placed on its back, which resembles some of the realistic scenarios. So maybe we can try to wave the phone or to do more motion with it to see how the algorithm perform with these different input responses. And maybe we can combine the gradient-induced technique with the thresholding technique, like have a combination according to maybe they provide improved performances. And maybe as well, in terms of the computation complexity, which we pick a platform and try to implement the algorithms to this platform and try to make a comparison of the computation